So we're going to continue our conversation on vectors, starting with scalar multiplication. I did mention at the end of our last video that when we talk about multiplication for vectors, it's a little bit more expansive than it is with numbers. As I was talking about last time, we have multiple notations for multiplication for numbers that essentially all mean the same thing as long as we're dealing with numbers. But as soon as one of those objects becomes a vector, they stop meaning the same thing. And even that statement of once one of them becomes a vector, this, which is going to be what our scalar multiplication is just a number, a scalar, something with only magnitude, being multiplied by a vector. Both these other two have to be vectors being multiplied together, either vectors being multiplied together in a dot product or vectors being multiplied together in a cross product, which again are both different operations. So you generally get one of three types of multiplications. Either some sort of scalar, some sort of simply a number, being multiplied by a vector, and that's going to give you a new vector. And we'll talk more about that in a minute. These two vectors will have the same direction, but not necessarily the same magnitude. And frankly, the only way for them to have the same magnitude is if that scalar k is 1. So generally, what a scalar multiple does to a vector is it changes its, scale, changes its magnitude, makes it either longer or shorter. When we talk about dot product takes two vectors, dots them together. Notice I can't say multiplies them together because you'd have to ask what type of multiplication, dot product or cross product. So we don't say we multiply these two vectors together. We either dot them or cross them. We either find their dot product or find their cross product. But its result is going to be some scalar value. When we dot two vectors, we don't get another vector, we get a scalar. And we'll talk more a little bit later about what that scalar is, but it's essentially a value that is proportional to how much those two vectors are working together. And by working together, I mean the direction they're pointed. So if they're pointed in the same direction, it's just the product of their magnitudes. If they're perpendicular to each other, or what we call orthogonal to each other, then the dot product is 0, regardless of their size. So it essentially gives you a sense of how well two vectors are working together. If we take the cross product, that does give us a new vector, and it gives us a vector that is orthogonal to or perpendicular to the other two vectors and has a scale proportional to the angle between, or the cosine technically, no, the sine. Yeah, the sine of the angle between those two vectors. So cross product tends to be a little bit more complicated and require 3 dimensions at least. So we'll not talk about cross product here, but it's important to keep in mind that these are very different operations when we talk about vectors, even though we're used to them all being interchangeable symbols for multiplication. That interchangeability only works when we're strictly talking about numbers. Okay, so again, what does scalar multiplication do? Well, if we've got some vector v, and say we want to multiply 3 times that vector v, well, it's one of our standard ways of thinking about multiplying. Multiplying is repeated addition is one of the ways we think about multiplication. So if we took this vector v and added it to itself 3 times, so that's vector v 3 times, then that result would give us a new vector that's in the same direction as v, but is 3 times as long. That's essentially what scalar multiplication does. If we wanted to take, say, multiply v by 1/2, okay, we'd get a vector that's the same direction as v, but it's half as long. So scalar multiplication tends to be nice, especially if we have something that is in position vector form. So say we have a vector 3, -4. And of course we could draw that. It's going out 3, down 4, so that's our vector 3, -4. If we wanted to take that vector and multiply it, say, by 5 times the vector 3, -4, well, okay, so it's going to be 5 of those vectors. They should all be the same length, technically. But if this goes, say, over 3, and we're doing it 5 times, then we're going to go over 3, and then over another 3, and over another 3, and over another 3, and over another 3. So we're going to go over 15. So it really is just like distribution. That 5 times the 3. And we're going to go down, well, each vector goes down 4, so 4, 4, 4, 4, 4. Our resultant vector is going to go down 20. Well, because that's the 5 times the -4. So multiplying scalars times vectors, or performing scalar multiplication, tends to be a fairly intuitive mechanic. It does what you think it should do. If you have 5 of those, okay, it's just 5 times each component. If you had half of them, half of each component, and so on. So the example we want to look at here is, given this vector 3, 1. So I'm going to draw that for us here. 3, 1. These could be bigger grids. We want to find, well, geometrically and analytically, what's 3 times v1? Well, 3 times v1 would just be 3 of those. So 1, 2, well, be a little bit lower than that, 3. So this result would be the vector 3 times v, given that little vector v. And if we wanted to do it analytically, in some ways it's even easier, because it really is just distribution. 9, 3, well, that's this vector. 1, 2, 3, 4, 5, 6, 7, 8, 9, up 1, 2, 3. Half v would be half as long as v, so instead of going all the way here, it's only going to go halfway. So it's really tiny, unfortunately, in this diagram, but it's just going to be half as long in the same direction, but half as long as v. So 1/2 v, if we wanted to do it mechanically, multiply the 1/2, 3 halves, 1/2, and that's our little vector, over 3 halves, up 1/2. So that's 1/2 v. Now we talked about the opposite of v as being v but pointed in the other direction. But really, that opposite of v we can think of as -1 times v. So it's going to have the same magnitude, but that negative makes it the opposite direction. So it's going to be pointed in this direction. So it's going to be that vector. And I guess that gives me a good excuse to clarify what I said. I said scalar multiplication will be going in the same direction. Technically, it will be going in the same direction or its opposite. So we'll be, along the parallel, that's the better word to use. Our vectors are going to be parallel, but their magnitudes are going to change. So if our scalar is negative, it is going to reverse our direction. So if we wanted to find the negative of v, it really is -1 times that v. So -3, -1. Oh, and I guess I had space to do it there. I kept thinking there'd be 2 other vectors that we'd have to do this with. So sorry, I squished that all in one place. But scalar multiplication tends to be fairly polite. To the point that we can get problems like this that, in some ways look like they could be a little, scary. Like, what is this asking us to do? It looks so serious. But remember, this is w equals 3. That 3 is just a scalar. Times u. Well, u is the vector -3, 2. Plus 2 times the vector -1, 5. And we'll talk a little bit later about why this is as intuitive as it is. But it really is just, do this like you normally would if these were, the sum in a set of parentheses. So our order of operations, scalar multiplication, still occurs before addition. So we end up with -9, 6, and -2, 10. And then again, like last time, when we add vectors, we're adding like components. So to be formal, -9 plus -2 and 6 plus 10. But we're just adding like components. And that's our W. So like I said in the last video, vectors have a lot of notation, a fair amount of vocabulary. They look weird, and that can take some getting used to. It can take a lot of getting used to seeing a problem like this and knowing what it's asking you to do. And that's about getting used to the vocabulary and getting used to the notation, getting used to what this says. But the actual mechanics of vectors tend to be pretty straightforward and pretty intuitive once we get used to that notation and vocabulary. So you really want to focus on that when we're dealing with these sections. Now, this word's come up quite a bit. I've been trying to kind of avoid saying components, but it slips in there every once in a while. I've been kind of referring to this as having components and whatnot. So we finally get to kind of talk about that. Why do I keep saying components? So when we talk about some vector, and I'm just going to use this one we had up here, -11, 16, this vector tells us how far essentially left and right. In this case, it's to the left, 11. The second piece tells us up and down. And so these are our 2 components of this vector. We have a left-right component and an up-down component. Those are our 2 different pieces that are constructing this vector. Now, this is for a 2-dimensional vector. If we had a 3-dimensional vector, we'd have a left, right, an up, down, and a forward, back. So we'd have 3 components. In a 4th dimensional vector, we'd have 4 components, and so on. So the number of components we have is the number of dimensions in our space, to think about it simplicity. Or simplicity. So when we talk about breaking a vector down or decomposing a vector down into its component parts, we're essentially talking about separating the left and right component from the up and down component. It doesn't have to be up and down and left and right. We can generally break them up into any pair that when we add them together we get the original vector. But up and down and left and right tend to be how we think in coordinate systems. So it's a natural decomposition. There can be other decompositions though. So if we wanted to break this vector W into horizontal and vertical components, well, the horizontal component is the -11 with, again, no up and down anymore. And the vertical component, so 0 in the first piece because it's not going left and right, but then 16 in the vertical piece. This breaks it down into our essentially 2 parts, a vertical component and a horizontal component. Now we'll talk about why we might want to do that or why we might want to think that way in a minute. But when we talk about components of a vector, that's what we're talking about. We're talking about those 2 pieces. Get this to go away. So if we want components of a vector with this initial and this terminal point, there's a couple of different ways that we could do this, but probably the nicest, given what we've had, is recall that we're going from 3, 2 to 7, 4. So build our position vector form, which every once in a while I've been calling component form because it's a form made up of the different components. Hopefully that seems reasonable. So we want to know how far do we go in this direction. Well, that's our 7 minus 3, the change in our horizontal position, so 4. And then how far do we go in this direction? 4 minus 2, again, end minus beginning, so 2. So this vector v as a position vector is the vector 4, 2. If we wanted to further break it down into its components, it's the 4, 0, that's its horizontal component, plus 0, 2, that's its vertical component. Now, one of the reasons we do this is because we want to start being able to think in what's referred to as ij form. And in 3 dimensions, it's ijk form. And what this does is it breaks us down into a single unit of horizontal movement and a single unit of vertical movement, and uses those single units to build up any vector that we want. So first, I want to talk about what I mean when I say unit and what we mean when we talk about unit vector. So a unit vector is essentially a direction, I'm going to say here, without, notice that's in quotes, I'm going to clarify that in a second, is a direction without magnitude. And I'm going to say sort of. So I put it in quotes and said sort of, so clearly there's some clarifying to go on here. if we made the magnitude of a vector 0, a 0 vector is certainly a thing. The 0 vector is a fine object. But if you don't have any magnitude, if you're just that dot, then you don't have a direction. It's not going anywhere. So if you want to be able to express a direction, but not have a magnitude that's contaminating that vector, not have a magnitude that is especially meaningful, if that magnitude was equal to 1, 1 is a very nice number that doesn't contaminate things. And think of it in terms of multiplication. If you multiply anything by 1, it doesn't have any effect. So it's not that it's without any magnitude, it's just a single unit of magnitude. So a unit vector, not necessarily more precisely, but yeah, more precisely, a unit vector is a vector of magnitude 1, hence unit vector. It's like our unit circle. It's a circle of 1 unit of radius. So it is a vector of magnitude 1, but its job is that it's meant to specify a direction. So often, one of the things we'll do, and we'll do some examples of this, is try to find a unit vector in a particular direction. A unit vector that heads the same direction as a different vector that we have, where the magnitude of that original vector is just turned into a magnitude of 1 to essentially remove the impact of its magnitude and specify only its direction in a meaningful way. So we're essentially taking the two parts of a vector. Remember, a vector has magnitude and direction. We can compute its magnitude with the modified Pythagorean theorem, and we can express its direction by making a unit vector in that direction, and then later we can combine that unit vector with any magnitude we want to make a new vector with the magnitude we want and the direction we want. So it's kind of breaking it down into pieces. So the unit vectors we're going to care about in a minute here are these two unit vectors that are given particular names, I and j, and they are the unit vector in the horizontal direction or x-axis direction. The unit vector in the horizontal or x-axis direction we call I. Now I'm going to modify that in a second. And the unit vector in the vertical direction, or y-axis, is given the name j. Now, these are vectors, so we'd think those vectors should have the little arrow on top, and they should. But there's an extra bit of notation that we often use with unit vectors to specify that a vector is a single unit in length. Instead of putting an arrow above it, we put these little chevrons above them. Now, we don't call them chevrons, though that is a technical term for the symbol. We literally call them hats, which I know sounds funny. So we really do read this I hat and J hat. And the hat specifies that it is 1 unit in length. So what this will allow us to do is express how far we want to go in the horizontal by how many eyes do we want, and how far do we want to go in the vertical by expressing how many J's we want. So it'll break us down into IJ components, horizontal and vertical components, by how many of these unit vectors we have in those directions. But before we do that, we've got to finish our talk on unit vectors, because I said we can find a unit vector in any direction. And I want to specify for us here how we do that. So any non-zero vector, again, it can't have a magnitude of 0, any non-zero vector, we can obtain a unit vector in the same direction by multiplying that vector by the scalar 1 over the magnitude of the vector. Now, what does that mean? So let's get some vector u. I'm going to make this a really nice vector. 3, 4. That's a very nice, very convenient vector. 3, 4. Now, I want to make a unit vector in the same direction as, well, this vector u. So if I want to make a unit vector in the same direction as u, I'm essentially wanting to build u hat. Now, these are different vectors. This is a vector u. It's got whatever magnitude it has. We'll find that in a second. And this vector that we're building should be going in the same direction as u. That's why it uses the same symbol, u. But the hat says that it will be going in u's direction, but only have a magnitude of 1. And we find that by taking this vector that goes out 3 and up 4, and essentially removing its magnitude. Now, if we wanted to find the magnitude of that u, we know we can find it with the modified Pythagorean theorem. So 3 squared plus 4 squared, that's 9 plus 16, it's 25. Square root of 25 is 5. So that's our, famous 3, 4, 5 right triangle. So the magnitude of u is 5. To make the unit vector in that direction, we're going to take our original vector and divide out its own magnitude. So there's a lot of symbology going on here. Notice this problem up here uses u's and v's because it can't specify the difference between u with the arrow saying the vector and the u with the hat saying a unit vector in that direction, because it's not using this arrow symbology up here. So it's one of the strengths of our formal symbology. But yeah, there's a lot of symbology going on here. So the unit vector in u's direction ION is found by taking the vector u and divide out its own magnitude. Now, why divide out its own magnitude? Well, we're trying to make it into a size 1. And what happens if you divide something by itself? Well, you get 1. Or at least, in our case, a vector of magnitude 1. So we know our direction is, our magnitude is 5. So we're going to take our vector 3, 4, and divide by 5. Well, we really don't have a division. We only have scalar multiplication. But again, remember, we don't need division because all division is just multiplication with fractions. So we can think of it that way. And then if we multiply that scalar, that 1 over its magnitude through, we will get 3/5, 4/5. So over 3/5 and up 4/5 will give us a new vector that is going in the same direction as u, but only has a magnitude of 1. So a vector going that direction with a unit magnitude. So a unit vector in u's direction. Now, again, this is not the vector u anymore. The vector u is 5 times as long. But this is going in exactly the same direction, and it's got the same it's got the new magnitude of 1 unit. And we could test both of those things. If we wanted to find the magnitude of this unit vector, well, 3/5 squared plus 4/5 squared, that's 9/25 plus 16/25 square root, that's 25/25, 25/25, which is the square root of 1, which is 1. So its magnitude is 1, just like we wanted. Also, if we wanted to find the direction, the tangent of 4/5 over 3/5, the b over a, well, if we multiplied both of those by our 5, multiply top and bottom here by 5, we'd get the tangent of theta is equal to 4/3. Well, that's the same thing we would get if we tried to find the direction of u. So clearly they're going in the same direction. We just built something going in that direction that has a magnitude of 1. So how do you find a unit vector going in the same direction as something? You just take that something and divide out its own magnitude, divide out its own size to build a 1. Now, often it's not something nice like 5. Often it's some fun square root you have to deal with, but we'll see examples of that. Like here, for example. Given this vector, 3, 1, find a unit vector in the same direction. Oh, and find a unit vector in the opposite direction. That's fun too. So, given v, a vector, 3, 1, I want to find a unit vector in that direction. So I want v hat, so that's a unit vector in that direction. And we do that by taking v, 3, 1, and dividing by its own magnitude. So I got to go off and find v's magnitude. So v's magnitude, and again, I use the double bar magnitude by years and years of habit. You feel free to use whichever one your instructor wants. But it's going to be 3 squared plus 1 squared, or the square root of 9 plus 1 is 10. So we're going to get our vector 3, 1 divided by its own magnitude, so the square root of 10. Now we could formally write that we're multiplying by 1 over the square root of 10, but we know what that's going to do. That's going to turn into 3 over the square root of 10 and 1 over the square root of 10. So that's our unit vector in v's direction. Now, to be polite, we should rationalize that. So 3 square root of 10 over 10 and the square root of 10 over 10. So that's our unit vector in V's direction. So again, if we wanted a vector with any magnitude we want, say I want a vector of magnitude 87 that's going in the same direction as V, well, multiply 87 times V hat, and that result will be going in V's direction and have the magnitude that we chose. Because multiplying by 1 doesn't change our magnitude. Now, if we want to go in the opposite direction of V, okay, I want a unit vector in the direction of V, but I want to go in the opposite direction of V, so have that negative. Well, that's just going to be the opposite of our 3 square root of 10 over 10 square root of 10 over 10 vector. So negative 3 square root of 10 over 10 and negative square root of 10 over 10. So really building a unit vector in any particular direction, you pretty much automatically get the one going in the opposite direction. If you want, just throw in your negative. Similarly, unit vector in the same direction as negative 5, 12. Well, again, if we wanted to draw that, negative 5, 12. So that would be our position vector. So our unit vector should go the same direction, but be only 1 unit in length. So that length would be 1 unit. So we're going to take the given vector V and divide by the magnitude of V. Well, this is one of our nice triangles, so negative 5 that way, 12 that way, a little Pythagorean theorem, and you know that magnitude is 13. So the natural magnitude is 13, so if we want one that has a magnitude of 1, we just take our vector and divide its magnitude by, well, divide the vector by its own magnitude, divide by the magnitude of 13. And we'd get negative 5 thirteenths and 12 thirteenths. So this is a nice example of a question that a lot of students struggle a lot with. This question, find a unit vector in the same direction of some given vector, is a very common question on tests to see blank. And you can see, hopefully, it's not difficult. It's just when you're not used to the vocabulary and the notation, it's really easy to read this question, find a unit vector in the same direction as V equals negative 5, 12, and not remember what it's asking or know how to approach it or what to do. If you know what it's asking and know how to find it, finding it's not hard, just taking that vector and dividing by its own magnitude. But knowing that that's what you have to do is what's hard. And that's why I'm saying for this section, focus on the notation and focus on the vocabulary, because the mechanics aren't bad, but knowing what to do when is what's hard. So don't let all the weird notation and all the new vocabulary throw you off or convince you that it's difficult. Just play with it. Okay, so we finally get to talk about full IJ vectors. So why we wanted these unit vectors and why we want these component pieces is because it's really common to build vectors out of these components. So this notation actually predates the notation that we've been using with the AB. So this notation was really common, this IJ notation was really common before this notation was common. So our notation kind of goes in that direction. We're kind of going backwards. There it is. Here. Which is fine, just something to keep in mind. So, if we have, say, a unit vector, I'm going to ignore the scale for a second. This unit vector I in that direction, I hat, and this unit vector j hat in that direction, we're essentially trying to represent vectors by saying, okay, how many i's does it take to make this? So this is 1, 2, 3, 4, 5 i's. So there are 5 of these unit vectors in the I direction, the horizontal, and then how many in the vertical? So 1, 2, 3, 4. Let's say all those are all the same. So 5 in the I plus 4 vectors going in the j direction builds this big orange vector, v. Now it's the same essentially as expressing it as the position vector 5, 4. It just has more notation in it, which is handy for certain types of operations. The nice thing is, it doesn't change any of our mechanics. If we want the magnitude of v, well, it's just the same. It's the square root of our horizontal component squared plus our vertical component squared. It doesn't change anything mechanically. So what, 25 plus 16 is 30, 41. Adding and subtracting are the same. If we have two vectors, say this 5i plus 4j, and we want to add another vector, negative 2i, say minus 6j. Well, if these i's and j's were, say, x's and y's, you would just collect like terms, right? Well, it's the same thing here. Bring like components together. 5i and negative 2i, so 5i minus 2i, well, it's going to be 3i. Hat. 4j plus negative 6j, so we're going to have negative 2j. So the nice thing about this ij form is that because it has the addition, subtraction, multiplication in it, it behaves a lot like our polynomials, all x's and y's do, and it makes manipulating it in some ways more intuitive, really, than even this 5, 4 notation did, or even the position vector notation. So if we have this u and this v, and we want to find 4u minus 2v, I'm starting to lose RAM here. If I wrote down the 4 times our u is 3i hat minus j hat, well, if it helps to write the 1 there, you can write the 1 there. We don't need it, but we know it's there. Minus 2 times v, where v is 2i plus 5j. And we want to simplify this. Well, yeah, this is vectors. This is a whole new thing. We got I hats and j hats. They're unit vectors. But everything you've learned up to this point in your mathematical career already tells you what to do with this problem. If these weren't fancy i's and j's, if this said, 4 times 3a minus b minus 2 times 2a plus 5b, and somebody said, simplify that, well, you would distribute, because you're distributing multiplication over subtraction, and distribute that negative 2. Be careful with the negative. And the nice thing is it's exactly the same way you handle these. That's one of the benefits of this ij form, is all of your mathematical intuition that you've built up, and then collect like terms, all that intuition you've built up is going to pay off. Collect like terms. So 8i and then minus 14j. Now, could we have done that in the position vector form? Yes. Would it have been just that smooth? Yes, in a lot of ways. It looks a little stranger because it doesn't have the nice distribution to it, but both systems work very well. One of the benefits really of the component form, this IJ form, is that it doesn't require us to be thinking in terms of position vectors. This 3i minus 1j can exist anywhere. So can the position vector, technically. So a lot of people are starting to de-emphasize this IJ form and just sticking with the position vector form, and that's fine, I guess. But a lot of folks will use this IJ form particularly us old school folks, quite often. The nice thing is, once you get used to one, you can usually handle the other. Okay, what do we got? We're on 46 minutes. Let's talk about trigonometric form, and then I'll put dot product on a different video. But dot product's a little bit weird, and I'd like to talk a little bit more about it. I'd like to expand a little bit on what dot product is. So I think that would be nice to do in a separate video. So, trigonometric form of a vector. Not as different as it might seem, really. We are used to, if we have some point out here in space, xy, at some radial distance r, we know that the sine of this angle is equal to y over r, and we know the cosine of that angle is x over r, and the tangent of that angle is y over x. Okay, we know all that's true. What this section is telling us is that if we have a vector that we express in standard position that goes to the point AB, so the vector AB, and recall the length of that vector is the magnitude of the vector. Well, notice this A is an x value, that B is a y value. That radial value r is how long this piece is. It's this hypotenuse of the triangle. They're not different lengths or different pieces. They're just different labels because we're talking in terms of vectors instead of talking in terms of coordinates. But they're the same object. So if we want to talk about this angle, the sine of that angle, well, it's still the horizontal component over the radial value or the hypotenuse. It's just, okay, now they're labeled differently. Magnitude of V. Or, here they even called it the y value. Okay. It's all the same value. That magnitude of the vector is an r. So don't let it throw you off the fact that now we have this new symbology. It's the same arguments that we've been dealing with for weeks, just, in a slightly different notation. So that really is our x over r and our y over r. So we're essentially saying here x is r cosine theta. Well, we've been dealing with that for a long time. And y equals r sine theta. Well, we've been dealing with that for a long time. So if we have a vector coming up here and we know these coordinates, let's say this is 9 and 12, then we can write it very easily in component form, 9i plus 12j. We can write it really easily in, position vector notation, 9, 12. Both of those are easy. And we could compute its magnitude using Pythagorean theorem, or we could find its direction using tangent. Okay. But if instead somebody comes up and gives us a vector, and instead of telling us the vector in terms of those coordinates, or the coordinates of the initial and terminal point, they tell us the magnitude of this vector is 15, and this angle is 40 degrees, it's not as obvious what that point is, and not as obvious what our I and j components are, and figuring out what those I and j components are is really handy if we want to talk about multiplying it by something, or particularly adding or subtracting. The nice thing, though, if we look at these tools, or r cosine theta, r sine theta, if we want this y value, that y value is our how many j's we have, well, we know how to do that. That's a sign question, right? So we know that the sine is the y over r, so the y is the r times the sine. So the component form, or the position vector form here, that magnitude times the sine of our angle is going to be our y value. The magnitude times the cosine of the angle is going to be our x value. So 15 cosine 40 degrees, that's our I component. That whole piece. Plus whatever the number 15 times the sine of 40 degrees is. That's some number. That's how many j components we have. And because, remove this, because this 15 is common in both of those terms, it's really common to think of it as having it factored out. So if we factor that out, 15 times the cosine of 40 degrees in the I plus the sine of 40 degrees in the j, well, then we have the magnitude of the vector, 15, multiplied by this cosine of the angle in the I plus the sine of the angle in the j. And again, we already associate cosine with x's and sine with y's anyway. And the fun part is we know what the magnitude of this vector part has to be, because we know what the square root of cosine squared 40 degrees plus sine squared 40 degrees. No matter what the angle is, if we want to find the magnitude of this thing, well, cosine squared theta plus sine squared theta's square root, cosine squared plus sine squared is always 1. So this is a unit vector in the direction of 40 degrees being multiplied by the magnitude that we want for this vector, 15. So if you want a vector with length 7, okay, its magnitude has to be 7. At an angle of 135 degrees, okay, cosine 135 degrees in the I, because that's the horizontal part, plus the sine of 135 degrees in the j, because that's the vertical part, that's your vector. Now that's what we would call trigonometric form. I'm going to abbreviate that trig form, because we've got the magnitude on the outside and then the cosine sine of the angle on the inside. But this wanted it in component form. Okay, to get component form, you're just distributing that 7. So 7 cosine 135 in the I plus 7 times the sine of 135 in the J. And technically, that's component form. Now, since 135 degrees is one of our standard angles, it is good for us to say, okay, that's the square root of 2 over 2, negative, because that's, what is that, 3 pi over 4 in the I, plus 7 times the square root of 2 over 2 in the J. So negative 7 square root of 2 over 2I plus 7 square root of 2 over 2J. But even if we couldn't do that, that's a component form of this vector. That's the trigonometric form of the vector, and that's the only difference. So if you're given magnitude and direction, you can build that component form very quickly by just taking that magnitude and multiplying by the cosine of the angle in the I plus the sine of that angle in the J. Then when you multiply in that magnitude, you suddenly have component form and can do all the adding, subtracting, multiplying, dividing that you want. But you've got to realize that that's what you have. And again, that's usually the hard part. Okay, we'll do dot product in a separate video, partly because this one's almost an hour, and I'd like to expand a bit on it. Dot product's a little bit weird. It's not, again, it's like most of the rest of this. It's not mechanically difficult. It's just new vocabulary, new symbology, and a little weird. So look for that, and we'll talk more in a bit. Until then, have a beautiful day.